So we are going to begin with using NOR gate. We are going to first learn how to draw the NOT gate. Same way. However, remember the NOR operation was, since it is opposite to OR, so A plus B whole complement, which is basically can be written as A NOR B. So this is the form what I am going to bring it algebraically. So for NOT gate, what do? We'll start. NOT of A can be simply be written as A complement. This can be written as A plus A whole complement, because A plus A, look at the OR law, is A. And that complement still remains over here. Now this is already in this form, so we can tell this to be as A NOR A. So when we design the logic circuit, so how do we get it? The logic circuit is pretty simple. We'll get it this way. See, bifurcating the two inputs, this is bifurcated. I don't need to put so many arrows just to make you understand. So if this is A, this is naturally A complement. So this is what we get for the NOT gate. Now we are going to try for the AND gate using the NOR gate. So let's start. A and B can be simply be written as A dot B. This can be written as A dot B double complement. Now what we are going to do? We are going to break the inner complement. So according to De Morgan's law, it is A complement plus B complement, and the whole complement still remains. So we have A complement plus B complement, whole complement. Now this is exactly in that form. So that is, we can tell this to be as A complement, instead of A complement NOR B complement. And just now we found the value of A complement, that is A NOR A. So everything gets converted to NOR. So A NOR A NOR B NOR B. Now if we try drawing the logic circuit, so what do we get? A. So this is my A NOR A. And now we are going to draw the B NOR B part. This is the B NOR B part, and this is again NOT out here. That's it. So this is basically A dot B, A and B. So this is the entire AND operation using only the NOR gate. Now what we are going to do is, we are going to learn how to create the third gate, that is, we are going to create the OR gate. Of course, using the NOR gate. So here, once again, we are going to start it in the same way. A or B can be said to be as A plus B, which can be written as A plus B double complement. Now once again out here, do not break the inner complement, because the plus will become dot and you cannot get back to this particular form. So what do? We write it in this way. Let A plus B whole complement be X. Therefore, A plus B double complement is X complement. This can be written as X plus X whole complement. So this can be written as X NOR X. This is what we got over here. Now we are going to substituting the value of X, we get, what do we get? We get, now for X, we are going to substitute this value, that is A plus B whole complement NOR, once again for X, A plus B whole complement. So what do we get? A NOR B NOR A NOR B, that's it. Isn't it pretty simple? So we got it that way. Now what we are going to do? We are going to draw the logic circuit corresponding to it. It's pretty simple. A NOR B, again twice. which is being NOT out here. So we'll draw the A NOR B first. So here what we have is A NOR B, which I'm going to bifurcate to represent two A NOR B's. So here I'm bifurcating, just the arrow to show you I'm bifurcating, and then again in the midst of it I'm going to again NOR it. See, we were able to create every possible gate using either a NAND gate and NOR gate, and it is really justified. Why? It is called the universal gate, because it is possible to create every other gate using either a NAND gate and NOR gate. And I believe you understood these concepts, and I believe you are keeping a note of everything, whatever I am teaching out here. Next, when we have a logic circuit, how do we draw either using a NAND gate or using a NOR gate? So this is the concept which we are going to learn. So we are going to learn designing a logic circuit using NAND gates only. Now suppose I'll just give you a random expression, A dot B whole component plus A dot C dot B. It's just a random expression which I've given you, and what we are going to do is we are going to draw this logic circuit using the NAND gate. Now one method is algebraically doing everything whatever we have learned prior to this. Using the NAND gate, we were breaking it and trying to bring it in A dot B whole complement form. We were trying to do that. That is one method which will be too big. What we are going to do is we are going to follow a very, very simple trick. First of all, we are going to see that whether this particular expression is in the form of sum of product or not. Sum of product. So here you see it's the product, and here we see it's product and plus is indicating the sum. So it is a sum of product expression. No doubt regarding it. So if it is that, we have no issues. However, if it is not, then what we are going to do? We are going to, in that case, multiply using distributive law and first bring it to sum of product form. And then we are going to do this. Now let's see what we are going to do. First of all, let me tell you the steps involved. First, we are going to draw the logic circuit normally using all the basic three primary gates. So there are three variables A, B, C. Remember, this is what we learned, A, B and C. We have learned how to draw logic circuit. So we have three vertical lines, and then what do we have? First of all, the B complement. So we have a B complement out here coming out, and AND it with A. So we are going to AND it with A. So this is what we learned. And then A, C, B, all the three variables are being extended. A, B as well as C. These are again ANDed. And finally these two are ORed. See, it's that simple. Now what we are going to do is we are going to convert each of this gate using NAND gate. Now look at the trick. This is simply a trick. This NOT operation can be converted to, it will remain as NOT only, but using NAND gate. Remember the symbol which we had drawn before. So what we are going to do is we are going to substitute this with a single NAND gate. See, because B not B is naturally B NAND B. So hence we draw the NAND gate out here. Refer to what we had already learned. Now let a circle represent some NOT. Therefore, if I put a circle out here, I am not changing the expression because we know that A complement is equal to A. So if I put a NOT out here, if I put a NOT out here, I am not changing the logic circuit. Similarly, I'll put a NOT out here and I'll put a NOT out here. That means I'm not changing the logic circuit. So here, what happens? We get two NANDs out here also. Now, the problem is out here. Suppose this is X and this is Y. So what is the operation we got? We got it as x complement plus y complement. This is what we got over here. However, we know that according to De Morgan, this means x dot y whole complement. So that means, isn't it NAND? Isn't it x NAND y? So what we are going to do is, we are going to substitute this entire thing using a single NAND gate. So that's it. That is the technique or trick of converting the entire logic circuit using only a NAND gate. Now, let me tell you in a nutshell what you are supposed to do. That means at the end of it, what is the moral of the story? How do we do? Now, after this, of course, you can redraw the entire logic circuit using the NAND gate. No doubt regarding it. However, let me tell you the trick. If the expression is already in sum of product form, then we don't have an issue. I already said that. If it is not, we'll simply multiply using distributive law to first of all bring it in sum of product form and draw every operation in the form of NAND. So what do? You see over here what I'm going to do. I'm not even going to think it this way. I'm simply going to write A, B, C. Now draw the three vertical lines. Now see over here, B complement. So first of all, we are going to bring the complement. Remember how we draw the complement using a NAND. So here we have a NAND operation. AND it with A. So here we are supposed to AND it with A. Although it's written AND over here, we are going to make a NAND over here. And the reason for it, I've already mentioned why such a thing happens. Now A, C, B, again from A, we are going to bring out here A, B, and C. And here it is ANDed, however, we are going to make it NAND. The reason is all obvious. And these two are again odd. So what we are going to do? We are going to bring these two lines, and instead of OR operation, what we are going to do? We are going to make a NAND operation. The reason I already mentioned why such a thing happens. So that's it. So this is the simple technique for creating a logic circuit using only the NAND gate. Now, one more expression I'm going to take and we'll try drawing it. Okay. Now, what I'm going to do is I'm going to show you another expression which we are going to solve using only NAND gates. That is A dot B plus C. Now, if you look at this expression carefully, it isn't sum of product which I was talking about. So, what we do first is we first simplify it to make it sum of product. So how do we do that? We simply multiply it, that is A dot B plus A dot C. Once we do this, we get a sum of product expression. Now we can draw every gate using a NAND gate. So it's pretty simple as that. So A, B, C, now you can do the usual stuff. So A and B, so A and B, it's written AND, but we are going to do NAND. A dot C, so A dot C, we are going to do NAND. Both these ANDs are again odd, so we are going to make a NAND gate once again. You see, pretty simple, I believe. And you know the rules also for construction. That is, how did we come into this conclusion? In a nutshell, whenever you get a question, you can draw every gate with the help of NAND gate, provided the expression is in sum of product form. So if you get a question to draw a logic circuit using NAND gate, you first check whether the expression is in sum of product form or not. If it is not in sum of product form, so multiply it using, of course, the distributive law. And once you get the sum of product expression, you can draw every gate using the NAND gates only. So this is how we construct a logic circuit using NAND gates. Now what we are going to do is, we are going to learn the construction of any logic circuit using NOR gate. This is what we are going to do. Now we'll try the construction of every possible circuits using only the NOR gates. So how do we do this? Suppose we have a mathematical expression of this sort, A plus B dot, suppose C plus D. Suppose if we have this. Remember, it's easier to draw the entire logic circuit using NOR gate provided the expression is in product of sum form. Since this is in product of sum form, so what we are going to do? We are going to draw it using NOR gates only. Now, before learning, how to do this, first of all, we need to understand why we can draw every gate using NOR gate. So the same rule holds true even out here. You can see what we have done with NAND gates, A, B, C, D. We take the 4 variables as input. Say these are the wires. These are the inputs shown by arrow. Then A plus B. So from A, we use a connector. These are all disconnectors. We have A, then we have B. First of all, we'll draw a normal circuit. And then C plus D. So C plus D. And then what do we have? We are going to draw the AND gate. This is what we are going to do. So this is your normal circuit which you have already learned. Now what we are going to do is we are going to try converting this particular logic circuit using NOR gate only. So how do we do that? First of all, we'll put a circle out here to represent a NOT. So if I put a circle out here and if I put a circle out here, that means the circuit is not, it isn't changing, because complement will keep the circuit as it is. Similarly, I put a NOT out here, that means the circuit isn't changing. So these two are NOR gates already. Now suppose this is X and this is Y. So what is the output we get? We get X complement dot Y complement. Now what is X complement dot Y complement? According to De Morgan's law, this is X plus Y whole complement. So that entire thing, isn't it the NOR gate? So we can convert this entire thing to a NOR gate. So here you see every gate has been converted to a NOR gate for construction of this entire logic circuit. So now whenever we get a question like this, we can draw every gate in the form of NOR gate. I can show you once again the same thing, but this time without making the intermediate steps. A, B, C, D. So what I'm going to do is, let me draw the lines, vertical lines first. Now A plus B, so we'll go for this. A and B, so A plus B, it's OR, but we'll draw NOR. And then what do we have? C plus D, C plus D, it's OR, but we'll draw NOR. And then we have AND in the middle, however, we'll use the NOR gate. So here we have the same circuit using only the NOR gates. So this is what we are going to do, provided the expression is in POS form. Now suppose a situation arises where you do not get an expression in the form of product of sum. In that case, what do? We once again, I said that most important law, it was distributive law. Using the distributive law, we'll first break the entire, the expression, the sum of product expression into product of sum, and after that we can apply the same technique. I'll give you an example. Suppose we have an expression, a Boolean expression with the following content, A dot D plus B dot C. So suppose we have a Boolean expression with the following content. Now you can see it is sum of product. So we cannot construct the entire logic circuit using the technique which we have learned. That is all the gates using NOR gates only, because the expression isn't product of sum, it is sum of product. So what we are going to do first is convert this entire Boolean expression to product of sum. So how do we do that? First of all, we'll apply distributive law. Remember the distributive law, A plus B dot C is equal to A plus B dot A plus C. We had learned this earlier, so we are going to apply this exactly. So imagine this entire thing to be A plus B dot C is A plus B dot A plus C. So what do? A plus B dot A plus C. We can do this. Now this one again we can apply the distributive law to break. This is A and this is B, this is C. So A plus B dot A plus C. That is how we are going to break it out. So B plus A dot B plus D. Similarly, what do we have? C plus D dot C plus A. Now that's it. We get everything, the entire expression in product of sum form. Now you can easily design the entire logic circuit using NOR gate only. And you don't need to worry because the expression is already in product of some form. So what do we do? A, B, C, D. There are 4 variables out there. Let me draw the vertical lines. And rest is pretty simple. A plus B. So A plus B means OR, but we'll draw the NOR gate out here. So here NOR. Then what do we have? B plus D. So B plus D. Then what do we have? C plus D. So C plus D. And then what do we have? C plus A. So from A we'll have 1. And from C. Now all of them are ANDed, but we'll draw NOR gate corresponding to it. That's it. We have drawn the entire logic circuit. This was the logic. So this was the Boolean expression which was given, and I had drawn the entire circuit using NOR gates only. Pretty simple, I believe, once you understand the technique. That's it. And now what we are going to do is we are going to find the Boolean expression corresponding to XOR and try to draw the XOR using the NAND gate or using the NOR gate. So currently what we are going to learn is using NAND gate, draw a 2-input XOR gate. So this is what we are going to do. So let's begin with the XOR truth table. So we'll start once again. I believe you remember what we had done with the XOR. Inputs and these are the outputs. So here what do we have? Suppose there are 2 variables A and B. So what do we have? 0, 0, 1, 1. I believe you remember the trick for construction of a truth table. And remember symbolically how do we write XOR instead of that plus. So this is 0, this is 1, 1, this is again 0. Now what we are going to do is we are going to draw the entire logic circuit for XOR using NAND gates. Now first of all we'll find the Boolean expression that corresponds to the XOR expression. Now we know that to find the Boolean expression that corresponds to any truth table we need to apply the sum of product method or product of sum method. Now since I asked you to create using NAND gates only, first of all we are going to try creating the entire Boolean expression using the sum of product expression. So what we are going to do, sum of product expression, what do we get? For sum of product expression, I believe you remember we were looking at those outputs which were 1. So here, which are the 2 ones? We have 2 ones as output out here. And here what we are going to do is we are going to find the minterms that corresponds to this 1. So 0 becomes complement. So what do we have over here? A complement and B is 1. So dot B. And look at the next one. This is 1, so we'll write A dot and 0, 0 means complement, B complement. We have done this earlier, remember? So here what we get is, we get a Boolean expression that corresponds to XOR logic. So now we have a sum of product expression. Now we can easily draw this using only NAND gate. So let's try drawing the entire expression using NAND gate only. So simple as that. Let's start. A and B are the 2 inputs. So we are going to take 2 inputs out here. Then what do we have? First of all, we have A complement. So A complement is A NAND A. I just go through the previous stuff, whatever you have learned, A NAND A. So how do we draw that? We draw it this way, A NAND A. Let me put the arrows out here only. A NAND A. And then what do we have? Dot B. So from B again, we'll have one more NAND gate. So here we have one more NAND gate and then we have A dot B complement. So from A dot B complement so here we have one more NAND, and then we have an OR in the middle, but we will draw the entire thing in NAND form because the entire expression is in sum of product form. And this is what we get. So the entire logic circuit is drawn using only NAND gate. Pretty simple, I believe. Now what we are going to do is we are going to try drawing the same logic circuit. That is, we are going to try drawing the XOR gate only using NOR gates. So this time we'll draw the XOR gate using NOR gates only. So we'll try this. Let me rub the remaining stuff. Now, for finding the NOR expression or the NOR logic circuit, for the XOR expression, what do we do? First of all, we are going to find the product of sum form. So product of sum we'll look at the zeros, and 0 will remain as it is. I believe you remember the construction technique for finding the product of some expression from a truth table. So what do we have? A plus B, and for this one, what do we have? Once again, A complement plus B complement. So we have a product of some expression. Now we are going to construct the XOR gate using NOR gates only. So how do we do that? We'll write A and B as usual. Then we are going to have those vertical lines. And then A plus B, however, we'll draw using NOR gate. So A plus B. So this is the NOR. And then what do we have? A complement plus B complement. So A complement, remember A complement is A NOR A, and then B complement is also B NOR B. Again, we have a complement. That means we have a NOR out here because we have an OR here. So we'll draw a NOR gate, and these two are again ANDed. However, we are going to make a NOR gate over here. That's it. So this is what we get. That is the entire XOR gate using only NOR gate. See how simple it is. In a nutshell, you need to remember that for drawing a logic circuit using NAND gates, we need to have the expression as sum of product expression. To draw any logic circuit using NOR gate only, what we are going to do is we should be having the entire Boolean expression in product of sum form. If it is not given, we are going to convert it. And remember which law was supposed to be most important among all the laws which you have seen over here in Boolean algebra. It was the distributive law. That is why I had put an asterisk, a star out there when we learned it for the first time. Okay, now what we are going to do is we are going to understand or learn the switching circuit. This is primarily used to understand, in real world how these logics are applied. That's the reason behind this. It consists of simply, you can assume it to be, a load, power supply, and, few switches. So basically these switches are supposed to check the openness or the closeness of a particular circuit. So this is what we are going to learn in the switching circuit. So we are going to learn all the three primary operations which we have learned, or the basic laws, that is AND law, OR law, and NOT law. Look at this. It's pretty simple. You get it in one go. So AND switching circuit, that is what we are going to learn. AND switching circuit. Now look at this. Suppose these arrows represent a switch. So this is how I'm going to draw. Look at this, and here what we have is the power supply, and we'll continue over here, and here we have a load. Say load may be a bulb or anything of that sort. and this may be a few cells. So what happens over here, look at the way it works. Only when both the switches are on, then only the circuit is complete, and therefore the current flows through the load, that is through the bulb in our case, and you'll find that the bulb is glowing. So only when both the switches are on, this particular bulb will glow. Otherwise it is not going to glow. So this is what happens with AND switching circuit. Now we'll try with the OR switching circuit. So in OR switching circuit, what do we get? OR switching circuit. In OR switching circuit, what we do is we connect these two switches in parallel. You see out here it was in series. You must have noticed this. So in OR switching circuit, we'll connect it in parallel, and we are going to get the effect of the OR logic. So what do? We connect two switches in parallel. So this is what we are going to do. And here we have the power supply. And here what we have is the load. Here is the bulb. Now you can see when either of the switches are on, then what happens? The circuit is closed and the load is used. That is, the bulb glows in our case, either of the switch or both the switches. In all these three cases, either this switch or this switch is on or both are on, you see the circuit becomes complete and the bulb glows. Now we'll go for the NOT switching circuit. Now this sounds quite peculiar, that when you switch it on, then the bulb is supposed to get switched off. And similarly, when you switch it off, the bulb is supposed to get switched on, because it is supposed to negate the entire logic. I believe you remember this. So we'll start with the NOT switching circuit. Whatever you are learning, this particular part, that is switching circuit, is what we actually apply or use in basic electronics. So since it is there within our curriculum, I'm just giving you a glimpse of this. Nothing much. So here we have the power supply, and here we have the load, and here we have the switch. And look at the way I placed it. Now you see when the switch is off, like currently it is in off state, so what happens? The current will flow through the load, and therefore when the switch is off, the bulb will glow or the load will be used. Now when you switch it on, what happens? Since the load will give more resistance, naturally the current will be flowing through this path, because it finds it much more easier, and therefore the bulb will switch off. So you see how simply we can apply the NOT logic even for a simple circuit. So this is what we practically do in basic electronics to implement the AND logic, OR logic and the NOT logic. And this is furthered into designing the different microprocessors and the different transistors which are included in the microprocessor. So all this applies these three basic techniques. That's it. Thank you for today. And let me tell you that all the concepts may not be very clear in the first go. It is not possible. Some of you are very good at it. You get things at the first go. That's good. Congratulations for that. But some of you might not get it because you are doing it for the first time. So I recommend that you go through the entire video once again. Each of the videos right from the beginning, you start going through the videos repeatedly until you get the concepts very clearly. And please remember the assignments which I have given. Please do solve it to make the concept more and more strong in your head. And thank you. And hope you liked all the entire class and you have understood the entire concept. And whenever I get the next class, we'll carry on with our discussion. Thank you.